want to say 6 meters. So that's 1,875 kilometers. That seems kind of impractical. Yeah, it says 1,900 kilometers. It's significant, you know, the significant figures and all. So what does this mean? This means if you're going to build a railgun, you need to make the magnetic field much bigger, or you need to make the current much bigger, or you need to make the mass of the projectile much smaller, or all of the above. You know, something, you can't do quite what's, because you can't make a rail gun that's actually this big, right? But the Navy has built rail guns that are, you know, not that big. They're, you know, I don't know. They're smaller than this building. And they can launch pieces of metal very, very, very fast. There's pictures. If you look it up, look, you can find it. The place where I was working before, when I left Liberty for a couple of years, was the place where they had that railgun. It's the Naval Surface Warfare Center, Dahlgren Division. All right. We haven't done any calculus today. That doesn't seem right. You know, there's got to be a calculus problem in here somewhere we could do, right? All right, maybe 71 is a good example then. I really did want to get I guess we're not going to get to chapter 28 today, unfortunately. This might be our last problem, unless I do it really quickly, but odds seem against that. I do think, like, generically speaking, magnetic field stuff is slightly harder than electric field stuff, just because it's never not three-dimensional. Like, it's always three-dimensional. It's just the cross product is involved non-trivially, and so, like, pretty much it's all three-dimensional. Uh-oh. I'm like, did I? Well. Phew. Okay, good. It could have been bad. All right, here we go. So let's see here, number 71, 2771, we've got this one requires calculus because the magnetic field is not uniform. It's got some kind of point dependence. What if B is not uniform? So we have a square loop of wire that lies in the xy plane. The loop has corners 0, 0, 0, so LL. And it carries a constant current, and the magnetic field has no x component, but has both y and z components. So the magnetic field is given to us. Okay, cool. So the magnetic field is given. So we're not the Ampere's law, and we're not finding magnetic. So remember, in chapter 27, magnetic fields are given; they're not derived. In chapter 28, we're going to learn the Biot-Savart law and Ampere's law, and so, like, chapter 28, we're going to start finding magnetic fields from moving charge, right? But this one, we're just given it. So B naught Z over L. And he says J hat, right? And what's next here? B naught V. Wait a minute, is that a, wait. B naught Y over L, K hat. All right, so I'm going to rewrite that as my preferred notation, which is there's 0, right? 0, comma, B naught Z over L, comma, B naught Y over L. In fact, I'm going to write that again. Like, let's simplify our life. We've got B naught over L times the vector 0, Z, and Y, right? So that's the given magnetic field. That's the given magnetic field. We're supposed to sketch the field lines in the YZ plane, and then part B, find the magnitude and direction of the magnetic force exerted on each of the sides of the loop by integrating as appropriate. Let me draw the loop. The loop is in the XY plane. So we've got all right, I'm going to move the camera over before I forget. So how do we, what's the formula that's at play here? How do we set up the integral? Like what's the concept going on here? I'm going to skip part A. I don't really care about it. I don't think it matters that much. So the loop here, and what are we told about the loop? There's a current flowing in the loop, is that right?
Yeah.
And it's flowing which way? Clockwise. Oh yeah, the picture's clockwise. Clockwise. Oh, clockwise, is that right? So like this? Correct?
Yeah.
So that's my eye. Right. So the fundamental rule we need to remember is that df, right, is I d, let's say L, cross B. df is I dl cross B. And the thing is, the dl vector, it's going to be different on each one of these four segments. Let me number them. So let's make we'll make this one number 1, number 2, number 3, number 4. All right? So each one of these, we want to write down what is dl, right? So number 1, dl, well, we must make dl go in the same direction as the current. That's the rule. So it's in the y hat direction, and we can think about it being dy. So we've got like 0 dy 0. Or if you like, you could write that as like dy times 0, 1, 0, if that'd be more comfortable. We could do that. Let's do that. That's number 1. Number 2, my dl vector is actually going to be like 1, 0, 0 dx, I think, because we're going dx. Yeah. Now, I think for 3, our dl should be equal to minus what it was for number 1, right? So we should have like, 0, minus 1, 0 dy, I believe. And for number 4, minus 1, 0, 0 dx. Does that seem reasonable? So then, what's df in each case? Well, work it out, right? So, and probably here is a good place to use the algebra of cross products as opposed to the determinant formula, because we're only dealing with like one-dimensional vectors. So the cross product we can just do with like direct computation. Let me show you what I mean. So here, df vector in the first case is going to be I, this is y hat dy Cartesian cross product with b, and b I'm going to write as, you know, b naught over L times z y hat plus y z hat. That's what this is, right? B naught over L z y hat plus y z hat. That's a formula in terms of the hats. See, that makes it easier for me to calculate. I mean, I could do the determinant cross product thing, but I think this is easier for this problem, so I'm going to do it this way. See, because if I do that, y hat cross y hat is 0, right? What's y hat cross z hat? It is x hat. Y hat cross z hat is x hat. So this just gives me I b naught over L, right? I b naught over L, y hat cross z hat. So I get a y dy x hat, because y hat cross z hat is equal to x hat. And then, like, what would df2 be equal to? df2, we'd have I dl, which in this case is x hat dx. Yeah. Cross product with my b naught over L, zy hat cross, this will be cross plus, the b is the same every time, right? It's the dl that changes. So see what happens this time? What's x hat cross y hat? Z hat. So I'm going to factor out the I b naught over L, and I'll put some parentheses here. So we've got x hat cross y hat is z hat, so that gives me a z dx. Z dx. And then x hat cross z hat is minus y hat. So I get minus y dx. Oh, my bad. I need to put the directions in. It was z dx what? Z dx z hat minus y dx y hat, I think. I need to double check my work. I'm sorry. Brain unfunctioning. X hat cross y hat is z hat. I've got dx times a z. Great. Then x hat cross z hat is minus y hat. I've got dx times y, so y dx. Okay. Now, this might simplify, though, because we should think about what the situation is here. There's some special terms and conditions for 1, 2, 3, and 4, right? So we may be making life too difficult here. See, because like for number 1, I have x equals to 0, right? For number 2, I have, what do I have? Well, I have y equals to L there, right? For number 3, what do I have? I have, I've got x equals to L there, right? How about number 4? I've got y equals to 0 there, right? So we should keep those in mind as we're setting up, because these integrals we're doing are done over those lines. and so I must impose those conditions as I'm doing the calculus. Does that simplify anything? Like F1, nope, not really. Nothing big gain there. How about dF2? Well, y equals L. So that's actually L when we do the calculation, right? I don't think anything else. Yeah, that's all I got to say there. Okay, so great. Continuing, what's dF3? We have minus y hat dy crossed with, you know, b naught over L zy hat plus yz hat, yeah? So this time, y hat cross y hat, 0. I like this one more. Y hat cross z hat is x hat, but there's a minus. So we get, you know, I b naught over L times minus y dy. And it was in the y hat cross z hat, which was x hat direction. dF4, we've got ourselves a minus x hat dx Cartesian product with, you know, b naught over L zy hat plus yz hat. But notice that in this case, what's y equal to? 0. So this piece is gone. Yay! So we only have to think about x hat cross y hat, which is z hat. And so we get minus b naught times I over L as usual. Z dx. And now what do we do? Now that we figured out the infinitesimal force for each little dl along each line segment, well, then we add them up. So like the force on one should be the integral from what? From 0 to L. I mean, I think these are all integrals from 0 to L, pretty much. So like integral from 0 to L of y dy. And I just factored out the I b naught over L times x hat, yeah? This integrates to L squared over 2, which gives me an I b naught L over 2 x hat. So that's the force on the first segment. I'm going to put away this projector because it's in my way. So then up next, F2 is, so 2 again, I think, trying to double check. Yeah, integrate from 0 to L. What was my F2, dF2? Z, is Z, what, is Z a variable here? What is Z equal to in this story? Which number was this? 71. 71. if z is equal to 0, I'm going to be like, wah! 71. So, wait a minute here. The y-x plane. Well, I think z equals 0. Z equals 0 in our context. Right? I mean, this whole loop, the whole thing, right? It's in the xy plane. So like this all together is where z is equal to 0. So any place I had a z, like this is 0. All right? I think that's the only place that the calculation's affected is right there, right? Okay. So oh, cool. Yay. Wonderful. Well, we just lost. Now we've only got 2 integrals to do, not 3. Yay. So integrate from 0 to L. We're in F2, right? So I've got what? I got a minus L dx. And then that, everything else is the I b naught over L y hat. So what's that give us? That gives us a minus LL, right? And L squared, and we still got division by the L. We're gonna end up, we should end up with the same kind, like dimensionally consistent stuff from each one of these integrals, right? If I can get these all on the screen. So, oof. What do we got there? We got minus I L b naught y hat, right? From that one. And then F3, the force in the third segment would be integral from 0 to L of minus y dy, and then we've got our I b naught over L, and then what do we got here? X hat, which gives me a, this integrates to minus L squared over 2, right? So we end up with a minus I L b naught over 2 X hat. So the net force, assuming I haven't talked myself into some error, and well, we'll find out, right? I sure hope we're right. This would be a miserable way to end a week. It would be wrong. That would be horrible. F1 was down there, so we've got a I b naught L over 2 X hat from that one. And then my F2 was minus I b naught L y hat. My F3 was minus I b naught L over 2 X hat. And then we decided F4 was 0. So if we're right, the X hat parts cancel, And we're just left with, you know, minus I B naught L y hat. I'm very scared to look. Oh, I just went straight to C. I ignored part B. I guess we can find out if I'm wrong on a particular part, right? Because it actually asks for 1, 2, 3, 4 for part B of the problem, yeah? It's right? Oh, that is a relief. Number, what was this? 71. So on the left, we have B naught L over 2I hat. On the top, minus B naught L J hat. On the right, minus B naught Li over 2I hat. And on the bottom, 0. And in total, minus I B naught L J hat. That is what we got. Woohoo! Hey, we can do calculus. All right. So with that, I think that should be enough of chapter 27 for in here. So next week we'll try to pick up with chapter 28, and hopefully I can go halvesies next week, because Faraday's law it usually gives you guys a little more trouble, and invariably I do tend to test Faraday's law. I don't know, like these problems working today, they're good problems, but there are better problems. So nevertheless, I think everything we did today it's good that we did it, you know. But I'm happy that we're done. Where was I? All right. Well, I'm gonna hit the stop button. End your suffering. There we go.